Hi folks, Astronomy Live here. I'm currently on vacation, sitting outside, but I wanted to do a brief video covering claims that the Earth's axis is shifted and is not what it should be. So you can find this claim on a number of channels recently, but here's one from the Nibiru channel, and let's just take a look for a few seconds here and see what it claims.
The Earth has an inclination of 23.5 degrees. I wholeheartedly believe that we have definitely surpassed that. Instead of a circular path, the Earth's axis is wobbling more and more, widening its path every year. The green dots signify this year, 2016. So you can clearly see that over the months during this year, this inclination has gotten bigger and bigger.
Okay, wow. Where to start here? Well, he's using a video which claims to show how Earth's axis has wobbled in the year 2016. And the data comes from basically a graph that monitors Chandler wobble. And you can see he mentions, I'm not sure how you pronounce this, wizarrad.com. And if you go to that site, you'll find this chart. And it does claim that Earth's axis is tilting strangely, tilting more than it should in dramatic ways. And somebody put together this video that claims to translate this graph into a graphical representation of how Earth's axis is actually moving. But this is completely wrong. What it doesn't show you is the scale of the X and Y axis here, which is very, very important. Now, you can find this data. It's freely available from the Earth Orientation Center here. And you can download either a text file that has all the coordinates from the years that you specify, and you can plot that yourself in your own graph, or you can have them plot it for you. And that's what you see here. Now, this is actually the exact same data that we just saw on this site. See this graph here? Covering from 2013 to 2016, it's actually the same data. But what's important to note here are the scale bars on the X and Y axis. Note the letters MAS. What does that stand for? That stands for milli-arc second. So if you're not familiar with what an arc second is, it's 1/3600th of a degree. And so a milli-arc second is 1/1000th of an arc second. And to put this in some perspective, 20/20 vision is the ability to resolve objects that are separated by 1 arc minute. What is an arc minute? An arc minute is 60 arc seconds. And so we're dealing here with changes that are measured in milli-arc seconds, fractions of an arc second, which itself is 60 times smaller than anything a person with 20/20 vision can even see. So, to put this in even more perspective, the pictures that I brought back from the Chiefland Star Party, those deep space pictures had a resolution of about 1.16 arc seconds per pixel, and that's with an 8-inch telescope. It sees things that are much, much smaller than anything you can see by eye, but even that telescope would be inadequate for seeing a change of this amount, measured in fractions of an arc second. So, we're talking here about a very small wobble, and it is a very normal wobble. This is known as Chandler wobble. And you can look it up. It's been known for a long time now. And it occurs every single year. And it varies from year to year. But what we're seeing here is completely within the bounds of normal Chandler wobble. And it does not correspond to a motion of the Earth's axis that is nearly as dramatic as what you see here in this video. It's too small to see by eye at all, let alone translating to a motion of the entire globe wobbling around like a top. Now, the Earth does wobble around like a top over very long time spans. The most predominant motion is precession, which occurs over thousands of years. And because of precession, the North Star has not always been the North Star, or rather there have been other stars that have claimed the mantle of North Star over human history. And in thousands of years, the North Star that we know as Polaris will no longer be the North Star. But this takes thousands of years, and it's a very small motion. It can be detected, though, even with fairly normal camera equipment. But trying to misread these graphs is not the way to do it. So how do we do it? Well, the first step is to take a picture of the North Star and the rotation of the Earth over the night. And that's exactly what I did last night, with a long exposure of the North Celestial Pole and the North Star. The North Star Polaris is the bright star you see here near the center of the image, and you can see all the stars appearing to rotate around that point, or rather, a point very close to the North Star. That point is known as the North Celestial Pole. Now, I took a crop of this image and astrometrically solved it, and you can see that here. It correctly identifies Polaris and other stars in the field, but what we really want to know is whether or not Polaris is where it should be relative to the North Celestial Pole. So how do we do that? Well, first of all, we have to figure out where the North Celestial Pole should be at the current time. And you can do that by calculating for precession. The North Celestial Pole, by definition, should be at 90 degrees positive declination. But that point moves over time due to precession. So we can calculate where that should move. And I actually have all the math laid out here. It's rather lengthy, but pretty straightforward. It's basically a matrix of trigonometric functions, and when you chug through it, you get precessed coordinates. So you can precess forward in time or backward in time. In this case, we need to find out where the North Celestial Pole should have been last night. So I plugged in the coordinates of the North Celestial Pole where it was last night, and figured out where it was back in the year 2000. And you can see those coordinates here on the left. On the right, it shows where that corresponded to at a time last night when the image was being taken. And you can see here in declination 89 degrees, 59 arc minutes, 60 arc seconds. This actually corresponds to 90 degrees positive declination, or the North Celestial Pole. But in J2000 coordinates, it's different, slightly, by a few arc minutes, and this is due to the slow but consistent motion of precession. And you can see that corresponded to 23 hours, 59 minutes, 34 seconds, right ascension, in declination 89 degrees, 54 minutes, 21.24 arc seconds. So, we also need to know where Polaris should have been, where the North Star should have been relative to the North Celestial Pole. And rather than just referring to NASA or some software, I'm going to show you guys what Norton Star Atlas shows. I have a copy of Norton Star Atlas with me. This is actually from a publication in 2004 of the Atlas, and on the page immediately following Chart 1, you can see a list of coordinates of major stars that were on Chart 1, including Polaris, right here, to the nearest arc minute, which is good enough for our purposes because, again, 20/20 vision corresponds to the ability to resolve objects that are 1 arc minute apart. And you can see its J2000 coordinates were 2 hours, 31.8 minutes, and positive 89 degrees, 16 arc minutes declination. So if we plug that in to the precession calculation spreadsheet, which I will include as a link in the video description, you come up with the following coordinates. So again, these are the same coordinates in J2000 that you just saw from the book, but due to precession, last night the coordinates of Polaris should be expected to be 2 hours, 52 minutes, 46.9 seconds right ascension, 89 degrees, 20 minutes, 17.6 arc seconds. And that distance from the North Celestial Pole is about 0.66178 degrees. So if we plug all of this in, here's what we get. Here is the location of Polaris predicted by Norton Star Atlas, overlaid onto the astrometrically solved image, which I will also include as a link in the video description. And then we have the green circle representing the North Celestial Pole's position as it was predicted to be last night due to normal precession. And you can see those coordinates over here on the left, just as we saw in the spreadsheet. I then set the radius of that circle to be equivalent to the expected distance of Polaris from the North Celestial Pole last night. And sure enough, the green line runs right through where Polaris is in the image, exactly as expected. And of course, the green line is also concentric with the circles produced by the other stars around it. Now, if you look back at where the North Celestial Pole was in the year 2000, just 16 years ago, you see that it does not quite run through Polaris, based on the expected distance of Polaris from the North Celestial Pole, as it was last night. And so this does show the effect of precession over time. But it's completely expected and completely consistent with the way the Earth's axis should be moving. So basically, the image I took last night proves that the North Celestial Pole is right where it should be, the North Star is still the North Star, and Earth's axis is not tilting out of whack. So I hope that answers the questions about that. If you have any more questions, please leave them in the comments. And again, I'll include the links to the astrometrically solved image and the spreadsheet in the video description. Thanks for watching. Clear skies, folks.